Hello students, this is lecture number 19, okay, and we have already finished chapter chapter 4 and actually chapter 5 as well. Okay, so however, today we will just take up some problem. So problem number 5.4 I will solve. Okay, so basically, as I have said earlier, the chapters 4 and 5 are such that they go hand in hand, okay, and hence when chapter 4 was finished, chapter 5 also finished along with that, and the remaining thing we will know while solving this problem. Okay, so we take a practical problem, from there we will understand so how to solve those problems. Accordingly, based on what we have studied so far, we can use them to solve these problems. Okay, so this example problem is something like this. So problem is, there is a bar, so which is something like this one. However, this is from A to B is like this one, and from here the area increases something like this, and then it is fixed. The other end is fixed like this. Okay, so point A is like that, this is point B, and you have point C here. Okay, so x axis, then there is a body force in this portion from A to B, and this body force B is given as 10 Newton per meter. There is a concentrated force here applied at B, which is P equal to 150 Newton. Okay, E is given to be as 2 times 10 to power 7 Pascal. Okay, and coordinates are given. So here this is x equal to 1 or xa equal to 1, xb equal to 3, and xc equal to 5. Okay, done. And then there are the how you have to solve. It is given that you have to solve. Okay, one thing more, A is given, which varies that. So for A, for this one from B to C, A is given as A equal to 0.5 x minus 1 meter square. Okay, so that means when x equal to 3, so when you have x equal to 3, then you get 3 minus 1, 3 minus 1, so becomes 2 times 0.5, that becomes 1 meter square. Okay, also given that the area in this region, so area in this region is given as A equal to 0.1 meter square, which is constant. However, area in this region is given as 0.5 x minus 1, so it varies from these values till there. Okay, now this is also given that we have to make number of nodes, how many number of nodes we have to make, this also given. So it's given that you have to take 3 nodes in the first element. So there is, this is element number 1, this is element number 2. Okay, so first element has node number 1 here, then you have node numbering given, global node numbering given like this one. So all these are given. So 1 is given here, 2 is given here. Okay, node number, global node number, and then we have 3 here, and then you have 4 here. And element is there are 2 elements. So one element is from here to here. So element number 1, and second element is from here to here, and this is element number 2. Yeah. So these are the requirement, and we have to solve the problems. And what do we have to find out? The questions are: construct the element body force matrices and assemble them to obtain the global force matrix. So basically we have to find out the force matrix. So F equal to what? So all first element, so we have to find out the element force matrix or force vector, and then the global one. So global ones. Then we have to construct the element stiffness matrices and assemble them to obtain the global stiffness matrix. So we have to get Ke, yeah, and actual the global one, that is K, that we have to find out. Okay. Now find and sketch the finite element displacements. So we have to find out the value of u, okay, then find and sketch the finite element stresses, and then you have to find out the stress. Yeah. Okay, so these things we have to find out. Okay. Okay, so this question represents many things actually, and some kind of it will summarize everything what we have learned, and while doing that we are also going to derive few things. Okay, so let's start with the element number 1. So element number 1 is it's given that element number 1 is 3 noded. So this is element number 1, which is 3 noded. Node the global number is 1 3 4. Okay, so and as we have seen earlier, we can take 1 2 3 like this one. So depending on how the local numbering, based on us, whatever you want we can do it, or you can write like 1 2 3 like this also. So anyway, now this first we will take element number 1, and we will see what is the element force vector, element stiffness matrix and all. Then we will take the other one, and similarly we can do it. Okay, now so we also have to relate with the problem itself, and the equation, as you know, remains as the strong form. I am going to repeat. We will start from the chapter 3 actually. You will see the how chapter 3 is applied here, chapter 4 is applied here, chapter 5 is applied here. Okay, so we have a strong form which is basically, so d over dx Ea du over dx, okay, and then b, okay, so b is a function of x, okay, is equal to 0. Here E can vary, A can vary, yeah, and so on. For the 2 elements, we can actually have that for both the elements. So we can take for element number 1, Also we can formulate element number 2, we can also formulate, or we can also see combined way also we can do, right. So finally what do we get it is if you see the element, let us look at the element number 1, and we have the 3 noded, we have like this only. How? Like this. Here we have B is given, which is constant, right. B is constant, B is given to be 10 Newton per meter, right. 10 Newton per meter is given, okay. And then as we have drawn earlier, so we will have F1 and F2 or simply EA du over dx, that we have at x equal to 3, we have, in this case we have EA du over dx at x equal to 1. Yeah. So because element number 1 varies from 1 to 3, and hence we have x equal to 1 and x equal to 3, those we can write down boundaries, and then we have B like this one. So when we are going to derive the weak form for this element, okay, so we can also go element wise to have this strong form converted to the weak form, because condition may be different. In first element we have B, second element there is no B, for example, right. Okay. So then what to do? Next we are going to from this one we are going to convert that is in the weak form, and weak form will be simply Wx, and we have do dx Ea du over dx plus B okay Bx dx equal to 0. Yeah. Okay. Or we know what to do, and finally what we will get? You will get W. Okay. So we have to integrate from 1 to 3, right. So we 1 to 3, and because this one is defined from 1 to 3 only. So from x 3 greater than 1. Yeah. Okay. So we have Wx Ea du over dx, okay, 3 1. Okay. Then we have minus 1 to 3 dw over dx Ea du over dx. Yeah. And then also we have plus Wx B dx, this is also 1 over 3, 1 to 3 and equal to 0. Okay. Okay, fine. Now in this problem at both the ends u is given to 0. So here we have u equal to 0. Yeah. So u is not given. Yeah. So equal to 0. So left hand side we can either we can impose 0, or we assume it is not given at right now, and when we are solving the global matrix, there we will put the value. So that also can be done. Okay. So that will be better, because that makes life much easier. You don't have to for every element you don't have to put, if some element is at the boundary, then you need not apply the boundary condition there itself. So boundary condition can also be applied in the global stiffness in the global matrix system with the global equation Ku equal to F. So right there also we can do. So right now we don't apply the essential boundary condition. We assume that neither u is given there nor f is given there, and we will impose these things later on. So we will just write these without applying anything. Okay, so what do we get? We get or so here we will have a W3, yeah, so W3, then EAU du dx, yeah. So what we get here is basically the we can write it here, this some equation here, right. So this is nothing but f, basically f3. So okay, so or we may not, or we don't write that also, it's okay. So basically just take this one, and then what do we find? We expand it, then we have W3 EA du over dx. So let's go like this. So we have W3 EA du over dx, yeah, and this is at x equal to 3 minus w1 and EA du over dx x equal to 1. Okay, one thing we should write here, this is, it has area A1. Let's write, because we have area, the for this area is given to be A, so it's write A1, and for the second one we write area A2, which is given like that. So we can distinguish between the two because A is different, yeah. So accordingly we can write EA1, 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 and so on, and here also write EA1, EA1, right. Okay, so done. Then we have plus, okay, plus, and then we get 0, not 0, this is 1, 2, 3 dw over dx EA EA1 du over dx. Okay, fine. This should be minus. Okay, so yeah, it should be minus. So okay, minus. Okay, okay, plus 3 1 2 3 wx bx d. Yeah, got it. Okay, so this is what we have. Now next thing is actually how the equation, all these things now based on what we find what we take u as, right. So we have to assume u here. I think we also have to write equal to 0. So we have that one. Okay. Now we have to take u element which is 3 noded. So we let's take 1 and then 2 and then 3, yeah, and so here to here we have 2, right. So, we can take this is as 0 0 or x equal to 0, x equal to 0, this is x equal to minus 1, x equal to 1. We can do it like this one. Yeah. Why? We can shift our coordinate system. Yeah. So, it is not going to make any difference, because everything is integration. As long as we integrate it correctly, it will be fine. So, instead of writing 3 1 to 3, we have to write minus 1 to 1. Yeah, and we have to define u as per this one. Then automatically we will use minus 1 to 1 and it will be all right. So, let us say this is our local coordinate system, which instead of having 1 to 3 is goes from minus 1 to 1, and the only difference is we will write everything like this one. We are going to write the length is the same, 1 to 3 length is same, hence there is no basically between this and this, just this is a constant transformation. One is based on here, the other will start from here to here, right. So, this is the okay. So, this one start from minus 1 to 1 and this system start from 1 to 3. So, just you add 2 to this system, you will get this system 1 to 3 system, right. So, linear transformation, hence there is exactly the same result we get, provided we have u and w defined on this one. These kind of things also we have done, and we know from those. And how we found out? We found out for this one, let us say u1, this is u1, this is u2, this is u3. And similarly, we can have a W1 here, W2 and W3, yeah, and we defined the U, right. Here Ux we can define it as summation of n, right, n x and u, so n I and u I, where I 1 equal to 3 in this case. Yeah, and where we also worked out last time the what the n should look like. So, this will be something like this, n1 x will be equal to so this will go something like, okay. So, let us do on the next page just. So, 3 noded goes like this one, right. Okay. So, 1 minus 1 0 1, this is node number 1, node number 2, node number 3, and we know that this will look like something like this. The n1 will like this is n1, okay, and n2 should look like this, and n3 should look like this one, n3, okay. So, in that case our, so this is n2, okay. So, equation becomes n1 is equal to half, we can formulate based on this one, and from here to here L equal to 2 basically, and earlier we have formulated in terms of L, here we can directly write because we know this. So, n1 will be simply equal to x times x minus 1, because n1 is 0 at here and here, hence if we put x equal to 0, n1 becomes 0, if x equal to 1, n1 becomes 0. So, takes care of that. However, when we have minus 1, you should get value 1. So, if you get minus 1 here and minus 1 here, so you get minus 1 multiplied minus 2 equal to 2. So, hence we have to divide by 2, right. So, So, we have to this one. So, N1 we get. Similarly, N2 we get simply x plus 1 multiplied by x minus 1. So, you can have minus 1 here, so minus 1 here. So, this becomes 0, x equal to 1, 1 minus 1. So, this also becomes 0. So, at the both the places becomes 0. At this one as 0, you have 0 here is 0 here. So, 1 multiplied minus 1. So, minus 1, so you get just minus, you put minus value here and you will be all right. Now, you have N3 similarly. So, we can N3 also we can see here N3 has to be 0 here and here. So, we have x multiplied by x plus 1. So, you see if you have minus 1 put here, so this becomes 0. So, N3 becomes 0 at x equal to minus 1. Similarly, x equal to 0 if you put it here becomes 0. However, at x equal to 1 it becomes 1 1. So, 1 multiplied by 2, right. So, 2, so you divide by 2 will be the 1. Yeah. So, we get N1, N2, N3 now. The next thing is simply getting the u values, right. So, u x becomes is equal to this one. So, summation I equal to 1 to 3, yeah, and then you have n I u, not this u but this u I, right. Okay. And hence the w x we can write of the same form, which goes from I equal to 1 to 3 becomes n I w I, yeah, big W I. Okay. So, that means we can have these equation accordingly we can find out, right. So, for example, this value is nothing, we can call this one, okay. So, we can call f, let us call it f of first element, this is the second one, this force, okay, and this one is this one is given by, if you look it here, this is the force, tensile force going like this one, yeah. So, if we take the force F, this we are calling it is equal to F element 1 at node number 2, yeah. Node number 2 means the second at okay, it is not node number 2 because we are writing, so we do not be confused. So, here we have global is 1 3 4, yeah. So, in local, in the local we are writing 1 2 and 3. So, we will write 3. So, this is F13, okay. So, local node number 1, sorry, element number 1, and this is the node number 3. This equation is the force, this is what this one is, which is the force will be, this one will be negative of that. So, we will write like this one. So, this is what is equal to this value. Here it will be F of force 1 of equal to, that will be minus E A, or you can write this is rather we should write like this one, minus of this is equal to this. Relation will be minus because our force we write positive this way, but a stress will be positive this way. Yeah. So this actually it comes from the stress term. So stress multiplied by area is the force, tensile will be positive. However, the just if you look at the force itself has to be, if convention of the force is positive, will be in the positive x direction. So that is why this will be minus F11 will be equal to this. However, here F13 will be equal to this one. So this I have explained also earlier also. Okay. So just to see that there are two point of view. One point of view will be from a stress point of view, which is positive when you have a stretching this side, these stresses are positive. However, the force, if you just look at this one, not looking at here, the force is negative direction. So here the force will be negative. So this F will be equal to minus this equal to this, or F1 is equal to minus this one. Yeah. So this value we can put it there, and you can see that what is the meaning, right. So what we get here, this one is F13. Okay, so F13, and this one is minus F11. Okay, so here we have multiplied plus, here also minus becomes a plus. So accordingly we have these terms. Without minus we have minus minus plus. So we will see these terms can come in some force vector, and we can just simply write F13 and F11, simply like that. Anyway, so we will come back to this now. The W3 is here, W1 is here. So okay. So what is the next thing to do? So we will put these values here one by one and see what is the meaning of that. So W3, when you say W3, okay, W3, and we know the whole thing is F13, right. So W3 and F13 is equal to, now the W3 is corresponding to basically in our n, in this one, in the local, this one is the global, this is global. So what we are writing here is our global system. Yeah, in global system we are writing 3 and 1. So if we, but we are writing W, U and W in the local system like this one. So we can, instead of 3 we can, since W is defined locally like this one, so we can write basically this is basically I will write in quote. Yeah. So this one is nothing but is W minus 3. So 1 W1 F13 in local coordinate system. Yeah, and this is equal to W1 will be, if you put it here, will be equal to nothing but n, what do you get? W1 is equal to what? W1, W at x equal to 1 is nothing but equal to W3, simply equal to W3. Yeah, so this will be equal to W3. Why W3? Because if you put it here, this becomes N1 W1, N2 W3, N3 N1 W1, N plus N2 W2 plus N3 W3. Now at this point, at x equal to 1 in local coordinate or x equal to 3 in global coordinate, here n3 is 1, all others are 0. So, n3 value of n3 is 1. So, what you get simply n1 is 0, n2 is 0, n3 is equal to 1 and multiplied by W3, right. So, what you get W3 multiplied by F13. Yeah. Okay. Similarly, we will get this point. You have minus, right. So, minus W1 du over dx multiplied by EA, and we said x equal to 1, which is in global. Okay. We wrote x equal to 1 in global, right. So, this will be equivalent to minus w equal to minus 1 and then EA du over dx, right. Okay. Okay, and this we call something else, yeah. So, we should write that also. So, this is x equal to minus 1 in local. Yeah. This is in local system. So, this is x equal to 1 is global system, x equal to minus 1 is local system, is the same thing. Okay. And this thing we call it minus of f11, yeah. So, equal to minus, this becomes simply W1, the same way we got earlier, right. So, N1 this W is given by equal to N1 W1 plus N2 W2 plus N3 W3, and you know that at x equal to minus 1 only N1 will be 1, all others will be 0, hence you have W1 multiplied by N1, N1 is 1, so you have minus W1 only, multiplied by you have this we called it minus F11. So, you get W1 multiplied by F11. Okay. So, we got this value. Next we have to find out this one. So, which one? This. So, dw over dx EA du over dx. What? This is 1, 2, 3. Which one? Global. Will be equal to, we know that we will have minus 1 to 1, yeah, and then dw dx. dw dx will be simply what? Will be here summation of dni over dx. So, I equal to 1 to 3 and yeah, then wi. So, that is what it will be, multiplied by EA multiplied by, we will continue here. So, again another summation of I equal to 1 to 3 dni over dx, or you can say j now, j and right, and then you have uj and then dx. Okay, so this is j. Okay, and this is in local. So, this one is local. Okay, so we are transferring that to from global. We wrote like this one while deriving, but finally we are putting in the local system. So, like this will be, this will be equal to, we can now write this, we call it B matrix, you remember. So, we had dx, this one we can write it like this, equal to we can take out W1, we have W1, W2, W3, we can take it out, and what we will get here is something like this one, W1, W2, W3, okay. And then we get a matrix K, which is the first element matrix, okay. And then we will have here U1, U2, U3, like this one, where K1 will be equal to what, like this, K11, K12, K13, then K, this is symmetric, so it will be K12, K22, K23, yeah, and then it will be K13, K23 and K33, like this, where K12 equal to, or sorry, Kij is equal to -1 to 1 and dni dx Ea dnj dx. And this we have already, we have derived all those things, we are not doing the first time, okay. So this we have, and we are going to now find out what is dn1 and what is dni over dx and so on. So, for example, if you have to find out K12, then how to find out? So, okay. So, K11, let us find out first. Okay. So, let us okay, before that I think good idea to have dn1 over dx equal to d over dx, and you have x over 2, and then you have x minus 1, yeah, okay. And hence when you have x equal to -1, this becomes -1, and -2 plus becomes like this one, yeah. So, what do you get? This you get half d over dx and x square minus x equal to half 2x minus 1, yeah, and then becomes x minus half. Similarly, dn2 over dx equal to d over dx, and you have x square minus 1, yeah. So, let us see that values, okay. So, here we have equal to minus x square minus 1, okay. So, actually 1 minus x square simply, okay. So, next will be x square minus 1 minus of that, so that at x equal to 0 you have minus 1 and multiply minus 1, so becomes plus. So, is equal to minus 2x equal to minus 2x, okay. So, dn3 over dx is equal to d over dx, and then you have x over 2 and then x plus 1, okay. So, again if you have x equal to 1, you have 1 here, 1 here. So, 2 times 1 divided by 2 is becomes 1. So, is correct, and then equal to half, and then you have x square plus x. So, you have 2x plus 1, which is equal to x plus half, okay. So, we got all the three derivative. Now, next will be, if you want to find out K11, you can find from -1 to 1, and this, so this will be x minus half square, because dn 1 over dx whole square, because 1 and 1 both, so hence you have like this, okay, times e times a dx. Okay, now e is, so we have E1 A1, okay, so A is constant for the first element, so hence this will be EA1, and then we have this, okay, so we get x minus half cube over 3 simply, right, okay, and goes from 1 to minus 1, okay, and will be equal to E A1, and then over 3, and you put 1 first, so becomes half power 3, and then you have minus 1 here, yeah, so this becomes minus 3 by 2, so basically you get half 1 over 8 plus and you will get minus 1 and minus 1 over 2, so minus 3 over 2, so you get plus 27 divided by 8, yeah, so you get like this, yeah, or K11, value of K11 will be EA1 over 3, so over 24 we can write, okay, so this 8 times 3, and then 27 plus 1 is 28, so multiply by 28 will be equal to simply EA1 multiplied by 7 over 6, yeah, okay. Similarly, we can find out all of them one by one, you know, so this is similarly we can, in a similar fashion you can find K12, let's say K12 will be equal to, if you see here, will be this multiplied by this, so you will have this and multiply this. Okay, by the way, we could have also used the Gauss quadrature to derive this one, right. So the K11, so here we have integrated the usual analytical way. If we have to solve it numerically, we could have done this as well. And how? So K11, so let's see, so K11, so using the Gauss quadrature, okay, so this is quadratic, and we know that for quadratic we have to use 2 point for exact one, yeah, so that we have seen, okay. So for exact, in the last lecture video we had for quadratic 2 point is needed, so 2 point, okay. So that means K11 equal to, okay, so we have 1 to minus 1, so very good, it's already in this form 1 to minus 1, so we can simply use this one. So we have EA1 is common, so we can take it out, so we have EA1, okay, multiplied by W1, which is W1, and then we have F, we had xi, so F xi1 plus W2 F xi2, and EA1 multiplied by W1 was 1 only, and xi1 was F1 minus 1 over root 3 plus 1 multiplied by F1 over root 3 is equal to EA1, and F minus 1 over root 3. Okay, so minus, so we have this, so we have put minus 1 over root 3 here, of a square of that. So we get multiplied by minus 1 over root 3 minus 1 over root 3 minus half, so minus half a square, and similarly we get here plus 1 over root 3 minus half a square. This is what the value will be, and rest is we just simplify EA1 multiplied by, we know that here if you say square, so we just get 1 over 3, 2 of them, right? So will be simply 2 times 1 over 3 plus 1 over 4. Yeah, that's it. Okay, so is equal to, we get, so 7, we get 7 over 12, so basically 14, 7 times 2 also 14, so becomes EA1 14 over 12, or is equal to EA1 multiplied by 7 over 6, or 7 over 6 EA1. So what we see, the same value whatever you are getting there, you are getting here. Yeah. So in computers is done like that. So basically I am trying to summarize everything what we have done from chapter 3 to chapter 5, everything actually are applied there in order to solve this. Okay, so similarly we can find out K12 and others. So let us see, if you want to find out K12, so this will be simply 0 to minus 1 to 1, and dn1 over dx EA1 dn2 over dx. So you put the values, and what will you find out? This will be simply, if you do it, it will be EA1 multiplied by this will be minus 8. So will be simply minus 8 EA1 over 6 over 6. Okay. Similarly, we put K13 will be equal to minus 1 to 1 dn1 dx EA1 dn3 dx. If we do it, what we will get is simply EA1 over 6. Actually, you did not have to actually find out K13, because you know that each row has to be equal to 0. So this becomes a K11 plus K12 plus K13 equal to 0. So if you know K11 and K12, which is EA1 over 6 7, then minus 8 EA1 over 6 plus K13 equal to 0, this simply tells you K13 has to be equal to EA1 over 6. Yeah, and similarly you can construct basically the already we know we have completed the first row, and hence we can replicate. Yeah, so basically this is like this. If you see here, this is symmetric. This is something like you can like imagine this as the K11 is nothing but if you fix this and you are going to free this one and you apply a unit displacement, whatever force is are there, they will be the stiffnesses. So this will be K11, the force you require to introduce a unit displacement, then the reaction force here will be equal to the K12 reaction force here will be K13. Okay. Okay, we all the reaction forces, however, we have calculated using the equation. So whatever we got the value, we are going to put it without putting any physics there, because if you apply the physics, then there is no force transmitted this side, you know, so because this is fixed here, so it will not be transmitted. But mathematically we found that if the force here is K11, which is equal to 7 EA1 over L, then there is a reaction force here which will be equal to 8 EA1 over L, and there is a another force here which will be equal to EA1 over L. Yeah. So basically whatever we get mathematically we have to put, not we don't apply the physics here, okay, simply because if you apply physics, actually there is no force here because all the forces will be taken up by this one. Okay, but since this one is free, so this is the one which is going to take up like this one. But still you can assume that, okay, let us say forces are given to its here is this much. So whatever remaining has to be balanced, and hence this value has to be EA1 over L, and which will be in positive direction. Okay, now based on this you can also construct, right. So we have like K1 will be equal to EA1, right, and then it's not L, but this is 6 here, 6, okay, so over 6, and what we have seen here is 7, and then we have minus 8, and then we have 1. Similarly we can have minus 8 and 1 here. Here we don't know, okay. However, you can see this way. Now you can apply little bit physics. Basically you can see this is right here, okay. So let's say you are fixing at here and here, okay. So this is point 1, 2, 3, sorry 2 here, 3 here. You are fixing these points like this one, and you are applying a unit displacement. So the force needed will be U2 will be K22, right. So what we will see that half will be supported here and half will be supported here. So whatever you value you get here, so you will get simply like this. So you have K22, and then you will have K22 over 2, and here you will have K22 over 2 here as well. So hence this will be K23 will be like this one, K21 will be like this, yeah. So and will be negative side, right, will be minus of that. So see here, this one is nothing but K12 equal to K21, right. So sorry, this is not, yeah. So this is K21. K21 is minus 8, we know that, right. So this is equal to minus 8 EA1 over 6, and hence this can tell you that the value will be K22 will be equal to what? We minus plus, and this 2, so that 8 times 2 16. So you get 16 EA1 over 6. So we get 16 value here. Everything has to be 0, so you can have minus 8 here, and then it has to be symmetric, so minus 8 here, and then this also has to be total 0, so this becomes minus 8, and remaining here this also has to be 0, this this has to be 7, so you get 7 here, right. So we have built the stiffness matrix for one element which is 2 unit length, right. You see, this is 2 unit length basically, yeah. So basically L equal to 2, L equal to 2, then you got like this one. If L equal to LE, for general purpose, if you have to find out the stiffness, then you can say for general, you know that the stiffness, it will be EA over L terms comes here, yeah. So here you can say the 6 is nothing but 6 times 2, 3 times 2, where 3 multiplied by LE will be the one you can. So you can write K dash is equal to EA1 over 3 LE, yeah, and then you can have this value 7 minus 8 1 minus 8 16 minus 8 1 minus 8 7, you can have like this, yeah. So this is for the 3 noded element, this is the stiffness matrix, yeah. So now that we have found out value of K1 matrix, yeah, so we can actually now see which all things are remaining. So we have this equation now. So W1, W2, W3 are arbitrary. So K1 we have found out, U1, U2, U3 we have to find out, U1 will be equal to 0 is given because it is fixed, right. So all those we can put it later on, but this equation we have already dealt with, meaning that we have out of components we have written this in a appropriate form, this also we have looked at, this is minus signs, accordingly we have see that, and now we have to work on this one which is going to give us the force vector, yeah. So this element stiffness matrix we have found out, this is now force vector we get from here. So we have Wx multiplied by Bx, okay. So W, this is again global, we are going to write in the local, yeah, and Bx is B is equal to constant there, so only W term will be integrated, okay. So let us see. So the last term is 1 to 3 Wx Bx dx, which is global, B is equal to, we have minus 1 to 1 and Wx nothing but I equal to 1 to 3, and then you have n Ix multiplied by constant B naught dx, okay, and which is equal to simply, okay. So this is W, right. So we have to multiply by W as well, so here it will be Wi, so Wi here which will be like this, yeah. So which will be equal to W1, W2, W3, and then we will have here value of what we call F B1, F B2, F B3, okay, like this one. Of course, this is for element number 1, so we can write 1, 1, 1 like this one, yeah. So but this is how it will be, where F B1 will be equal to minus 1 to 1, and this will be n I x and B naught dx BABI is equal to. Yeah, so for example, if B1 will be, in this case will be minus 1 to 1, and we write N1, N1 is nothing but half x, and then x minus 1, right, and then B naught a constant, so dx which will be equal to B naught over 2, and either we can use the Gauss quadrature, or since we are working here analytically, so we can analytically also integrate. So this becomes x square, so x cube over 3 minus x square over 2 and 1 minus 1. Okay, so what we see here is this x square term. So this is even function, hence the value will be 0. Yeah, so only this will be working. So simply we get B naught over 2 and x naught, so B naught over 6, and then we have 2. So from here we get 2. So 2 times 2, so simply we have B naught over 3. Yeah, so right here is equal to B naught over 3. Why 3? This is because this term L0 value, this one will have 1 minus 1, 1 minus 1, so that's equal to 2, so this value will be 2, so 2 and 2 cancels out, so we have 3, so B naught over 3. Okay, and similarly if B2, so if B2 will be equal to dn2 dx, so not dn2, just n2, so n2 x dx B naught dx minus 1 to 1 will be B naught, and n2 is minus 1 to 1, n2 is minus 1 minus x square dx. Okay, so that at x equal to 0 value is 1. Okay, and then we have B naught, and we have x minus x3 over 3, 1 minus 1, yeah, will be equal to B naught, and we have 2 minus 2 over 3. Okay, so we have B naught 4 over 3, okay, so equal to 4 B naught over 3, and similarly if B3, either we can find out or logically also we can see. So what it tells you is there is one element here, and then we have B naught value goes like this one. It is telling you that the forces, this system, basically distributed force of B naught is being equivalent to the case where you have only 3 forces, one force here, one force here, and one force here. So these two are equivalent, and this is FB1, FB2, and FB3. So basically it tells you FB1 plus FB2 plus FB3 has to be equal to B naught times length is 2, so has to be 2 times B naught only. Yeah, so far if B1 is B naught over 3 and if B2 is 4 B naught over 3, so if you add these 2 becomes plus B naught over 3, so that becomes 5 B naught over 3. So FB1 becomes, you can say FB3 becomes equal to 2B naught minus 5B naught over 3. So that becomes simply is equal to B naught over 3 only. Yeah. Okay. So either you can calculate this way also, you can do it. This some sort of physics is there. Basically, the meaning of this kind of integration, when you have B W, this actually what it does is, from the continuous system it is converting into discrete system, meaning that from the continuous B, which is constant throughout this length, it is actually putting them at only 3 points. One part will come here, second part here, third part here, but the total force will be equal to the actual total force due to this distributed load. The distributed load is B naught and length is 2, so this is B naught Newton per meter multiplied by 2 meter, and hence this will be 2B naught Newton, right? So and hence distributed will be the one we either you can calculate this way here. So either we can say minus 1 to 1 B naught N3 x dx, which will, if you do, you will find out it will be B naught over 3 only. Okay. So we got the stiffness. You have to find out the stiffness matrix. So for this element, you can write the equation basically, and that equation will be first K, right? So K1 U1 equal to F1, where K is equal to E A1 over 6 in this case, and we get 7 minus 8 1 minus 8 1 16 minus 8 minus 8 7 multiplied by U1 U2 U3. Okay, so this is for the element local system, we can say local system. Okay, equal to, we have F1 F2 F3. Okay, so local system, so you can write as 1 1 1 like this. Okay, so F1 1 1. Okay, fine. So where F11 F12 F13 is equal to, we have to now, so this is assembly. If we assemble them together, putting everything as per the equation that we have seen earlier, so this equation, this whole equation now I am going to put into a single matrix. Yeah, so this we will put, so you see here, this will go this side, this whole thing, this minus here, the whole thing will go this side. So this will constitute K times U part here, and since U is only in this one, all others we don't have, here it is in the form of F, so U is actually not there, here also in terms of F only. So this will be K times U, and this will be F. So we are constructing F from here. Okay, so this we know that this one is nothing but W3 times F3 F13. So this one go in the third row. Okay, this term minus becomes plus, and this is W1 is actually goes to W1. This goes to W1. So here this will multiply to W1, and hence this goes like this. Here F11 will go to the first row. So first row will go this, second, third row will go this one, and remaining we have F1, FB1, FB2, all those things will be coming from here. Yeah, and then W1, W2, W3 will be common in all of them. So the final equation, the will look like something like this. Okay. The final equation will look like something like this one after getting rid of W. So we also have the W term here. So we can write like this. Here we have W, uh, transpose. Okay. So where W equal to W1, W2, W3. So we have transpose of that. So this will be common to all of them. Yeah. Okay. Now this here F1, F2, F3 will be, as I said earlier, there will be one which is coming from, this will be F1, 1, this will be F1, 3, then plus you will have F1, B1, FB2 plus FB3. Yeah. Okay. So which is equal to FB1, as we seen this is B naught over 3 only, so we can write B naught over 3, yeah, plus F11, B naught, this is 4, 4 over 3, 4 B naught over 3, and then B naught over 3 plus F12. So we have like this. So we got the F from here. So this one we got from the one where we wrote these values, this from the distributed load. So this is the final equation we got for the first element. Okay. So now we have to work for the second element, and that we will do in the next lecture video.